Hello friends, the topic for today's video is Huffman coding. It's a greedy based technique to actually perform data compression. Now data compression is a very important topic wherein you try to reduce the size of your data file. Now you may get a question that how do you achieve this? How do you actually effectively do the data compression? Now, we will learn about that in details in this particular lecture, but to go to the history, this particular algorithm was first proposed by David A. Huffman when he was a student like you at MIT. Now, before starting with the algorithm and how it works, let us first try to see how to represent your data in terms of binary code. Now, this is called as encoding. Now, encoding is nothing but assigning a unique binary code, a sequence of bits that is called as a code word. Each symbol is assigned a unique code word, right. So, we generally have three kinds of code words. We will be learning that: fixed length, variable length and prefix code. Okay. So, we are going to use prefix code that was invented by David Huffman for Huffman coding. Now, let us try to understand this in more details by taking an example. Let us say you have got a data file, a file which is having around 1 lakh characters. So, in that data file there are 1 lakh characters, and let us assume that we only have 6 unique characters repeating in that file. We do not have more than 6 characters, and those 6 characters are A, B, C, D, E and F. And the frequency of each character is given here in thousands. So, we have 45,000, A is repeating 45,000 times, B is repeating 13,000 times and so on, alright. So, if this is given to you and if we consider that each character is represented as 1 byte, like in C programming each character is generally 1 byte, okay. Now, if each character is 1 byte, that is 8 bits, and there are 1 lakh characters with you, right. So, you will be needing how many bits for your data file? The size of the file in that case would be 8 times 1 lakh, that is 8 lakhs bits. So, this is your data file, size of your data file. This is big number, right. 8 lakh bits is a big number. Now, can we reduce this? Can you reduce from 8 lakh bits to something lesser than this? And if you observe closely, yes you can, because I have told you that in this problem we just have 6 characters and you will not require 8 bit to represent 6 characters. So, if you want to represent 6 characters only, then 3 bits are sufficient, right. So, how do you find out 3 bits? So, you have 6 characters, you take log of 6 at base 2, you find the ceiling of this. So, this is around 2 point something, the ceiling of 2 point something is 3. So, by using 3 bits we can represent actually 2 to the power 3, that is 8 symbols, but we just have 6 here, right. So, if we take 3 bits we can represent uniquely. So, let us say that is this, we are giving a fixed length code for each of these bits. So, let us say A is 000, B is 001, C is 010 and similarly F is 101. So, 110 and 111 we are not using it. So, 3 bits in this example, 8 bits in this example, right. Now, both of these are fixed length code. Each character is having a fixed length code. In the first example 8 bits here, in the second one 3 bits, right. So, if you take 3 bits here, we just need 3 lakh bits to represent the entire file in contrast to 8 lakh bits. So, we have improvement here, right. But the question is, can we do better? Can we make something lesser than 3 lakh bits in this problem? Let us see in details. Now, Huffman actually proposed the idea of variable length code. This is the most important concept of Huffman coding, right. So, what he thought was, so here this is a greedy technique. He became greedy in deciding how to choose the code length. So what he said was, the frequently occurring characters you will be giving a shorter code, and infrequent characters you will be giving longer codes. Alright. So, like in this example he has A, right, A is occurring 45,000 times, frequency is high. So, he would give shorter code length for A and maybe a longer code length for F, because F is only occurring for 5,000 times. So, this is the idea of Huffman coding. This is the most important idea. Now, let us take the same example. We have A is occurring 45,000 times. So, let's because if you are writing, if you are assigning in terms of bits, you can assign 1 bit representation to A. Let us say A is represented by 1 and D 16,000 times represented by 0. This is our assumption, and B is represented by, let us say, 0 1 and C is represented by 1 0. So, we are given a variable length code, we have assigned it randomly, right. Now, but there is a problem in this way, because there is a problem in this. We will see what is the problem. Now, let us say I would like to encode AD. How do I encode AD? Is very simple. A is 1 and D is 0. So, it is 1 0. So, AD is nothing but 1 0 in terms of binary, if we follow this coding pattern. Okay. So, now let us say this is encoding. Now, let us say we have to decode 1 0. So, 1 0 should be decoded back to AD, right. If AD is 1 0, 1 0 should be AD, very obvious. Now, but 1 0 can be represented, it can be represented as AD, but 1 0 can also be C, because see, the code for C is 1 0. So, it will be confused, is 1 0, will I convert this into AD, or will I treat this entirely as one particular value and make it as C. So, it is confusing. So, this is ambiguous, right. Single code should not have two different sequences. So, there is a problem in this particular way of working. Okay. So, to avoid this confusion, Huffman proposed something called as a prefix code, which is a very interesting concept, which is the core concept of Huffman coding, prefix code. Now, let us see what is a prefix code. It is very simple. No code word, like in prefix code, no code word is a prefix of code word of another symbol. We will try to understand what does it mean. So, let us take the same example, why the previous example does not satisfy the prefix code condition. Now, previously we have assigned A as 1, D as 0, B as 0 1, C as 1 0. Here the prefix code property is not fulfilled. It is because if you look at the symbol A, it was coded as 1, right. But if you look, 1 is a prefix of C also. Similarly, D was coded as 0, but 0 1 is the code for B. So, this code word, this is the code word for D, and this is the code word for 0 1 is for B. Now, no code word is a prefix of the code word of another symbol. This is the another symbol, but this code word D is a prefix of B. This is not allowed. Okay. So, if one code is 0 1, I can't have another code as 0 1 0 1, because this is the prefix of this code. Similarly, if I have 1 0 1 as one code, I can have 1 0 1 1 1 as another code, because 1 0 1 is a prefix of this particular code. This is 1 0 1. So, this is the previous example is not satisfying the prefix code property. Okay. Now, let us talk about Huffman coding. Now, in Huffman coding we are supposed to identify the unique prefix code for all the symbols, that is based on the frequency. That means, higher the frequency, the code length would be smaller, shorter, lesser the frequency, the code length would be longer. Okay. So, you apply the greedy method invented by Huffman. Now, the idea is quite simple. We are going to make something called as Huffman tree. It is a binary tree. We are going to create a Huffman tree, which will follow the following properties. So, in a Huffman tree, I am going to work out the example for Huffman tree, okay, but the property is very simple. In a Huffman tree, we are going to make a tree like this, right, a tree like this, binary tree, to generate the prefix code. I will explain how, but all the leaf nodes in this tree would be the symbols, the characters, that is A, B, C, D, E and F. All the nodes would be having a frequency. Each node is going to have a frequency also, how many times that character is occurring. I have already told you frequently occurring symbol are close, this is the root. Frequently occurring symbols will be closer to the root and infrequently occurring symbols would be far away from the root. So, let us say this is infrequently occurring symbol and this is a most frequently occurring symbol, this one. Always on the left edge we will write 0, on the right edge we will write 1 for each node, okay, and the path from the root to the leaf will give us the code word. We are going to demonstrate this, do not worry. Okay, let us take this example. The same example, character is given to us A to F and the frequency in terms of thousands. One more thing, we will be using something called as minimum priority queue to solve this problem effectively. Alright, I am assuming that you already know what is a minimum priority queue. Okay, so first thing first, step number 1. So, first we need to create a 6 nodes, because there are 6 characters, we create 6 nodes. You know what is a node in a tree, right? I am talking about a node in a tree, right? Node is going to have a value, it is going to have a left subtree and a right subtree. We are going to create 6 nodes for each symbol with frequency as its attribute. Each node is going to have a frequency, okay, and we are going to place all these nodes in a minimum priority queue. So, priority queue is a queue in which we are giving a priority based on the frequency. The key value is the frequency. Okay. So, we create, so these are the 6 nodes F, E, C. So, I have sorted this is a minimum priority queue, right. So, I have sorted this in terms of frequency. F is occurring 5000 times, E is occurring 9. So, I have created 6 nodes like this. Okay. So, these are 3 steps. Then I need to do something where I need to repeat something. Okay. So, I will explain this by doing an example. Okay. So, let us begin. So, first step number A is done, create 6 nodes. Now, step number 2 is very simple, extract the 2 minimum frequencies from this particular priority queue. So, the 2 minimum, first one is 5, second one is 9. Okay. So, out of these 2, I need to create one node out of these 2 nodes. So, I need to merge F and E and create a new node. Let us say the new node is created. Okay. The frequency of new node would be 14, because I need to sum the frequencies of F and E. So, 9 plus 5 is 14. So, I have created a new node 14. The left subtree of the new node contains F, the first one that was extracted. So, I remove this from the queue. So, this goes as a left subtree here F, okay, and second one goes as a right subtree, this is E. Both of these are removed from the queue. And the left edge of the new node, the left edge is marked as 0 and the right edge is marked as 1. So, these 2 are removed and this is created. Finally, I need to insert this new node in the queue. So, if I insert in the queue, 12 is the minimum. So, this C comes first here, then 13, B comes here, next is 14. So, this new node that is created comes here, and then next is 16. So, it comes here, and then 45 it comes here. Now, I repeat the same step, right, until I am done with all the nodes. Okay. Okay. Now what I do is I have 12, 13, 14, 16, 45, extract 2 minimum. So 2 minimum are 12 and 13. So I create a node out of it. So 12 plus 13 is 25, the root. At the left I will give 0 as a path, A's value, 1 here. At the left I will get C, at the right I will get B. So 25. So these two are removed. I need to insert 25 in the queue. So first I will get 14 as it is here. This is removed, this is removed, 14 here. Then I get 16, then 25, then 45. Okay. Slowly I am generating the code word. Next. Now what I do? Now I am in step number C. Now I take 2 minimum. So 16 plus 14 is 30. So 30 comes after 25. So 25 is copied here. This 2 sum is 30. Left I will put this entire node, left 14 wala. At the right I will have D. Okay. I will copy this as it is. Now from this, how do I get this? Because I will add 25 and 30, I get 55. So 55 will come after 45. So 45 is copied first. Then 30 plus 25 is 55, the root node. At the left I will get 25 and everything. So I will copy this entire thing here on the left, this entire thing on the right. I am still having 2 nodes, so I need to do it one more time, the last time. So for the last time I will add. So if I add, I get 1000. So this is 100. So this is not 1000. This is 100,000. 100,000 is nothing but 1 lakh, because I had 1 lakh characters. 1 lakh characters. Okay. At the left, I will put A45, and at the right, I will put this one. So if you look at this closely, the characters, the symbols which is having the higher frequency are closer to the root, like A is closest to the root, and the one with the lowest frequencies are farthest from the root, like F and E, 9000 and 5000. All the leaf nodes, leaf node, leaf node, leaf node, all the leaf nodes are the characters, right. Now from this we can find the prefix code for each character. So this is the final step, this is the last step of your algorithm. Okay. Now I can trace to find out the code. So how do I find out the code for A? I start from the root and go till A. If I go this path, I will find 0. So the code for A is 0. How do I find out the code for C? From the root I will go till C. So this is 1 0 0. C is 1 0 0. So what is B? 1 0 1. B is 1 0 1. What is D? 1 1 1. D is 1 1 1. What is E? E is 1 1 0 1. What is F? 1 1 0 0. If you look at this, all these codes are prefix code. None of the code is a prefix of some other code, like 0 is not a prefix of, see, none of other code are starting with 0. None of other code are starting with 101, see. So there will be no conflict, there will be no confusion. So this is your final Huffman tree. This is what you should create. Okay. Now let's see how much of compression we have done. How much of compression we have done? Let's do some analysis. So in a fixed length code, we gave a 3 bit for each code, but in Huffman coding we have got a variable bit length. Okay. So if you talk about the fixed length code, average code length is 3. All of them are 3 bit long. Average code length is 3, and total bits required is, there are 1 lakh characters. 1 lakh into 3 lakh bits in this. This we have already done. Now let's talk about Huffman coding, wherein we have a prefix code. Now 45,000 times A is occurring. The length of code length of A is 1. So 45 into 1, 45,000 bits required for A. For B, we have 3 bit for each character. So 13,000 times we are having B, 13,000 into 3 number of bits for B. Similarly, 12,000 into 3, then 16,000 into 3, 9,000 into 4 and 5,000 into 4. So, we will have 2,24,000 bits required. If you use Huffman coding, we require lesser number of bits than the fixed length code. So, this is compression, we have compressed, right. So, from 3 lakh bits we have now required only 2,24,000 bits to represent the same data. So, this is data compression, right. So, what is the average code length in this particular case? So, total we need 2,24,000 bits, right, and we have 1 lakh characters. So, I divide 2,24,000 with 1 lakh. So, I get 2.24. At an average, each bit is of size 2.24. Okay, this was fixed length was 3 bits long, this is 2.24 bits long. Practically this is not 2.24 bits is not possible, but this is just an idea. So, how much percentage compression I have done? Previously I had 3 lakh bits required minus 2,24,000, this much I have saved out of 3 lakhs into 100. So, I am finding the percentage. So, I have found out it is 25% compression is done, it is a huge number. So, using Huffman you can actually go from 20 to around 80% compression by looking at the type of the data and the type of the file. This much compression you can do it using Huffman coding. Alright, so this is data compression. Now, let us quickly look at the algorithm, how it works. Okay. So, I have taken this algorithm from CLRS book, okay, and C is nothing but the set of characters, like this is A, B and so F. So, these are set of characters. N is number of characters, Q is my priority queue, wherein I put all my characters initially in a priority queue. So, creating a priority queue, building a priority queue will take big O of n time. So, I run a loop for all the nodes, I run a loop. So, this loop will run n times. Okay. So, this is number of times I am doing merging. So, if there are n elements or n characters, I will be doing merging operation for n minus 1 times. So, this loop is running for n minus 1 times, but asymptotically n times. So, what I do is I create a new node Z. So, I create a new node. Extract min is a function of a priority queue. So, I will extract the minimum from the queue, right. Let us say I make it as x. So, I will put that on the left of Z, I am putting x, and right of Z I am putting y, okay. And the frequency of Z is nothing but the frequency of x plus frequency of y. So, this is done here. So, whenever I am doing extract min, this is dq. So, x and y are removed from the queue. So, now I have created a new node Z, I need to insert that in the queue. So, this is what I am repeating, right. This is what I am repeating again and again. Finally, I will return the root of the node. Extract min will return the root of the node for the last time. This is outside the loop. If you look at this closely, extract min, you can use heap to implement minimum priority queue, right. So, in minimum priority queue, extracting minimum will take log n time, okay. Similarly, insertion will also take log n time, creation will take n time. So, total time is this is the time for creation, this one build max heap, and n log n is the time for the loop runs for n time. Inside the loop, the operations run for log n time, because these operations extract min log n time. So, n into log n is n log n. So, it is big O of n plus big O of n log n. So, asymptotically this is big O of n log n. So, this is the whole idea of Huffman coding, and I hope you have understood the concept. If not, then you can comment on this video. Thank you.